The last method, which sort of belongs to this block, is called multi-reference CI. That is, in a way, a bit an alternative to this RAS STF. And it is, again, or it is the attempt to treat not only static correlation, for which MC-STF is the optimal method, but also dynamic correlation. And the reason why I say it's an alternative for RAS to this RAS STF, because you can also do that in RAS STF. You sort of have your active space, which gives you describes the static correlation correctly, and then you include in this RAS3 space a lot of extra determinants, and then only allow single and double excitation to those. Then you will also get dynamic correlation included, as much as many determinants you allow to be included. This is a similar way of, has a similar goal. They want to also include both. And what you do is, actually, you do an MC-STF with a reasonably small active space, or very small active space, just the ones which are really necessary to get the chemistry right, to treat the degeneracy or the static correlation. So it is a two-step procedure. And then in the second step, you do a CI where you include, and that depends on what kind of CI you want to do, where you include double excitations from your reference wave function. But in a normal configuration interaction, your reference wave function is the Hartree-Fock, it's the single determinant Hartree-Fock wave function. And you have then signals or double excitation, triple excitation, whatever you want to include. Here you do a CI from the MC-STF, the one which we got in one, STF reference wave function. So let's take the simple case that we had the MCF included two configurations. That beryllium with the 1SW occupied, 2SW occupied, and the 1SW occupied 2S singly, 2P singly occupied. You had two configurations. Then here in the CI, I would include in my CI wave function now all singly double excited determinants which I get from exciting from those two configurations. And in that step, in the second part, it's a real normal CI, so I don't change the orbitals any longer. Here I adjust the orbitals to this smaller MC-STF wave function, and then I do a CI. So it's a bit like CI, except that the reference is not a single determinant, but it's an MC-STF wave function. Which also means, of course, that then the CI space is going to be larger, and one has to sort of be more careful with sort of truncating it. So maybe including all double excitations will not be possible anymore. And you say, okay, I include all double excitation, two orbitals up to that orbital energy, or something like that. Or you in some way you try to pre-screen which excited determinants to include by making a cheap Möller-Blechett calculation to figure out how large their contribution would be, and then you include them. So it's a bit more work to do to figure out which determinants to include there. But that is sort of potentially a very, very accurate method to a lower cost, significantly lower cost than doing a full CI. My full CI is the exact result. And there actually for a full CI calculation, it doesn't matter how you determine the orbitals, because you include all determinants anyway, And then that wave function is completely invariant to a transformation of all the orbitals. Whereas in all truncated, of course, the orbitals make a difference. If you change the orbitals, you get a different result. But that's a good way to do that.